Hello everyone. In this video we'll be reviewing the first law of thermodynamics and heat. So the first law of thermodynamics states that energy is neither created nor destroyed. However, it can be transferred from one system to another. And so we symbolize change in energy as this equation here. Delta E is equal to Q plus W, where Q is equal to heat and W is equal to work. So Q is equal to heat, and W is equal to work. And so if you want to talk about the energy transfer from one system to another, you could write that as this equation here, where we have delta E A for system A is equal to the negative delta E of system B. So this equation here is how you would symbolize the change in energy between two systems. Now, if we want to talk about the exchange of thermal energy between two systems, we can represent thermal energy in terms of Q, because heat is nothing more than the transfer of thermal energy between two systems. So we can rewrite the equation that we just wrote by plugging in this into E. And so our new equation will look something like this. So we'll have QA plus WA is equal to negative QB plus WB. And here all we're doing is substituting that delta E with Q plus W. For our intents and purposes, we can assume that we're in an isolated system where no work is being put in. So if we eliminate work, at least for right now, if we eliminate work, that means that we can further rewrite this expression of the exchange of thermal energy as the heat of system A is equal to the negative heat of system B. So then if we actually want to use this expression to solve for something, we have to even further extrapolate this formula. And so we have to define Q in terms that we can use to solve for something. So what I'm going to do now is write out the formula for Q. So we can define Q as mass times specific heat times delta T, which is change in temperature. So M is equal to mass, usually in grams. So typically the mass will be measured in grams. S is equal to the specific heat which is different for each individual compound. Different compounds have different specific heat measurements. The specific heat is derived from the thermal energy required to raise 1 gram of any substance by 1 degree Celsius. And of course, T is equal to temperature, either Celsius or Kelvin. And this equation is what we'll use to substitute for Q in both of these cases. So the formula that we'll use in general chemistry for measuring the thermal equilibrium between two systems, the thermal energy transfer between two systems, is going to be M of A times S of A. Sorry, that's getting a little small. Times the delta T of A is equal to negative M B times S B times delta T of B. And this is how we will measure that thermal energy transfer between two systems. So sort of tying it back to this concept of the first law of thermodynamics. If our goal is to measure the temperature at which the thermal energy of two systems is at equilibrium, we will need to use this expression here. So let's do an example to show how this would work. So let's say we had a beaker filled with ethanol. So CH3, CH2, OH. So we just have a beaker here of ethanol, and let's say it's 50 grams worth of ethanol in this beaker. So we have 50 grams of ethanol, and it is at 25 degrees C. Right? So we'll call this system A. So system A is 50 grams of ethanol at 25 degrees Celsius. Then we have system B. And system B is water, H2O. And let's say we also have 50 grams of this. However, this water is at the boiling point, 100 degrees C. So this will be system B. So what we're going to do is we're going to dump this boiling water into this room temperature ethanol. So our question that we have to solve is, what is the final temperature of the solution when we mix 100 degree water with 25 degree ethanol? So what we'll do is we'll use this relationship here to solve for the final temperature of the solution at thermal equilibrium. So the first thing we'll do, we'll treat this as A and we'll treat this as B. So we'll just start plugging in numbers. So M of V is 50 grams because that's our mass. So our mass is 50 grams for A. So we'll have 50 times S, and so the specific heat for ethanol is 2.46 joules over grams times Celsius. So we'll have that 2.46 here, and that's our specific heat. That's our S for ethanol. And like I said, specific heat will be different for each compound that you use in these kind of problems, and it will always be given to you. So S will always be given to you. And so now we're into the delta T part, but what we want to do is we want to break apart delta T, and we want to rewrite that as TF minus the initial temperature. And so our initial temperature of the ethanol is this 25 degrees C. So TF is our variable minus 25. And we're going to set this equal to so we'll have this negative sign out here. Our mass of water is also 50 grams, so we'll put this 50 here, times the specific heat of water, so SB is equal to 2.06. And this is the specific heat of water. So we'll put that here. And we're also going to tear apart delta T, and we're going to rewrite it as TF, so final temperature, minus our initial temperature, which is that 100 degrees. So we'll put that 100 here. And so now what you want to do is do some straightforward math. You'll want to distribute this 50 and multiply it to that 2.46. Same thing over here. You want to take this negative 50. Remember, there's a negative sign there. And you'll want to multiply that 50 to that 2.06. And so what you'll end up with on the A side is 123 times TF minus 25 and on the B side you'll end up with negative 103 times TF minus 100. So now what you want to do is distribute that 123 to the TF and to the second term. Same thing on this side. You want to distribute that negative 103 to the TF and to the negative 100. And what you'll end up with then is 123 TF. Remember that TF is our variable that we're trying to solve for, minus 3075, and this will be equal to Do the same process on the other side. You'll have negative 103 TF plus, and it'll be plus because we're multiplying a negative by a negative, so we end up with a positive. $10,300. So now what you want to do is combine like terms. So to combine like terms, we will add this 307.5 to both sides. So we will add this 307.5 to this side. And then we will add the 103 TF to the other side. Because remember, our goal is to isolate this TF. So I'm combining two steps in one here. So what we will end up with is 226 TF is equal to this. Once you add and subtract the like terms. Our goal, remember, is to solve for TF, the final temperature. So we'll divide by 226 on both sides. And so when we do that, your TF is equal to around 59 degrees C. So this is the temperature at which thermal equilibrium is established by combining these two things. And that is how you would solve a thermal energy problem in the context of heat transfer. And you'll get a final answer out, and make sure you include your units in degrees Celsius. And there you go.